Okay, let's present. Okay. Okay. So yeah, thank you, Vincent, for this nice opportunity to show you my results. You will see. So the first thing, in all of these talks, you've seen how nice nuclear spins are and so on, and they have really high coherence times. What my topic was to connect these nice systems to mechanical resonators. You will see in a bit what these are and how this works. So the nice analogous system to these to the system I want to look at is the optical system of an atom in an electromagnetic cavity. You have some electromagnetic mode caught in this cavity, so you have electromagnetic resonances, and you put an atom, some electronic spin into this cavity and couple these together. And this is very well described by the James Cummings model. But the thing what we could do then, instead of using this two-level spin on half, is use a nuclear spin. So we can potentially have up to 9 levels instead of just 2. On the other hand, you can also say this is a nice way to couple this potentially even chaotic system with bosonic modes, right? But what's the regime we actually want to achieve to measure this? This is called the strong coupling regime, and this requires the interaction timescales, or the coupling frequency between the atom and the electromagnetic mode to be much stronger than the losses of the electromagnetic mode to the outside and the spin to the outside. Right? This is given by this inequality. Right? Okay. So in total, we can look at if we have this, we can look at the coherent dynamics between the phonons and the spin. Okay. How does this look like if we use, instead of the electromagnetic mode, a mechanical mode? We will have to use mechanical resonators. What is a mechanical resonator? You can basically take any mechanical object that vibrates in some way and cool it down, for example, to near the quantum ground state. So you can think of this as a harmonic oscillator being quantum coherent. The shape of this is a very active field which typically couples these modes to optics. And these resonators have very different shapes. So examples are in this cantilever, the frequency is 1 megahertz. There is also thin beams, you see it only very faintly. There's also like these very interesting toroids, also membranes, or even microscopic dumbbell resonators, which are also interesting. And you see the frequencies are typically in the megahertz regime, sometimes higher, sometimes lower. And the quality factors can be quite high. So what we think we would need for quantum coherent experiments is more in the range of 10 to the power of 6. And you see these are quite close to that. Sometimes less, sometimes higher. Depends on a bit on the shape. And the materials are also can vary a lot, but silicon is also definitely possible, which is important for us. Okay, how does this experiment look then? So we can take, for example, thin beam resonator and put the atom in there at a good position as before with the cavity and the mirrors. And what we need then is first silicon, because all the properties you had with the nuclear spins are best known in silicon, but typically this can be any group 4 material where you can extract all the natural nuclear spins. Then you have to apply a magnetic field to separate the levels of the nuclear spin. And you have to implement some readout electronics, maybe in superconductivity, maybe some optical means. I will mention this in the end. Okay, but what's actually the coupling mechanism between these two things? Right? In the electromagnetics, we have the dipole term. Here, what's the coupling? This is actually done by the spin quadrupole interaction. Vincent has mentioned this before. I won't want to go through it again, but if you want to know more, just ask. So this is the full term. So we have the sum over a product of two nuclear spin operators with this quadrupole strength tensor. And this strength tensor depends on a few things, but mostly the most important for us here is that it depends on the electric field gradients. Right? It's also a tensor classically. And if you go further, this electric field gradient tensor is just the second derivative of the electric potential. Right? You can calculate it classically, or in the end you will have to use DFT, but this is the important part. And we want to connect everything to, we want to connect to the mechanical oscillation, right? So how does this connect? We have to look into the microscopics of this. So we have the silicon lattice around here. So this is an antimony donor, but the symmetry is the same for a few other donors in the silicon lattice. And you can either apply shear strain or an electric field. And in both of those cases, you will distort those bonds and create a local electric field gradient. If we put this in formula, the electric field gradient tensor is then depends on these two components. The first one is the strain, right? That modifies the gradient electric field tensor by this gradient elastic tensor. This is just a fourth order tensor to translate basically from the strain, which is the second order tensor, into this other second order tensor. This is just mathematics right now. It gets simpler if we have a specific geometry. On the other side, we can also use an electric field, which is just a vector and needs to be translated into a tensor, so we have the third order tensor. These can be either measured or also calculated, but yeah. Alright. So what we have is strain that couples to the gradient elastic tensor that couples in the end to the Hamiltonian of our energy levels of the nuclear spin. Right. So how do we drive now our nuclear spin? So in the end we want to have both be coherently connected, so in the end mechanical oscillation has to drive the nuclear spin. If you want to drive a spin in general, you always have to apply an oscillating Hamiltonian with the frequency of the spin transition, right? So that means that we have to modulate the Hamiltonian with this, for example, cosine term. Then, from that, we usually get a Rabi frequency, right? And this is determined by this matrix element with the two nuclear spin levels that we want to have the transition between. If we plug in all the things we just had, this HQ is the spin quadrupole interaction I just showed you. We just summarize everything. We get out this very large term, and very important, the strain modulation is involved. So if we sinusoidally modify our strain, we can drive our nuclear spin between two spin levels. Okay. This is already really nice, but still, I would say, quite complicated. You cannot really see how strong this interaction will be at one glance. You have to look at a specific geometry. And one attempt of this, if you simplify, set the best possible magnetic field direction, if you go to a silicon crystal and have the orientation of the crystal as everything is perfect, and you will end up at this Rabi frequency, right? You have material-dependent factor, which depends on this gradient elastic tensor component. It's only one, because we have turned our crystal lattice in the right way with respect to the magnetic field. This is the nuclear quadrupole moment, which comes from the correction to the nuclear spin. The nuclear spin number, and also this matrix moment, which just comes from the spin matrix elements. And on the other hand, we have this resonator-dependent term, which also depends again on the way the mechanical mode is placed in the mechanical resonator, and these terms will have a certain magnitude dependent on the geometry. Okay. What we have to realize here, I always only talked about strain modulation, but for our model to be quantum coherent, the coupling is determined if this strain relation is given by the 0-point fluctuation, right? So the smallest strain fluctuation you can have on our mechanical system. If this is the case, then this Rabi frequency is our coupling frequency, right? So to get strong coupling, just a reminder, we have to set the strain fluctuation to be the 0-point fluctuation of the mechanical resonator. So I'll just call it here epsilon z as 0-point fluctuation. Okay. Now that's clear. I want to show you first how to maximize this material-dependent feature. And for that, we unfortunately don't have so much data. The only data we have so far, which is also mostly due to the work of the Modell group, is the data on the three donors, arsenide, antimony, and bismuth, and the neutral atom germanium in silicon. With other host materials, we don't have any data yet. You see, these have nuclear spin numbers between 3½ and 9½, and then the gyromagnetic ratios, that will be relevant later also, are in mostly positive, but sometimes also negative. In, for example, in the highest with 7 and in smallest with 1.5. Also here the nuclear quadrupole moment is also varies. It's the highest for antimony, and these two random elastic tensor components are actually the only ones that are active in silicon. Also vary between these two atoms and are highest for bismuth, typically. And also the shear component is much higher than the axial strain component, which just means that, which is only relevant for the orientation of the magnetic field to the crystal lattice. So if we put all of these factors together, we get this factor is in this line here. And you see that we expect the coupling for bismuth atoms to be the highest and the lowest for germanium atoms. But also antimony is also quite okay. Arsenide is less again. But yeah, so this is something we can keep in mind. So I can only show you data for example, germanium, and we can just have to multiply these results with another factor. Okay. Questions so far? Yeah.
Can you repeat the note? This 1,1 and this 4?
Yes. Can I go back here? So it's better to see here. Right. You have maybe a little bit more. Here. So this S tensor is the translation from the strain to the electric field gradient. And in silicon we have a lot of symmetries. So in the end you only have S11. So do you know Vogt notation? Vogt notation? Okay. This is 4 indices. But you can summarize them because of symmetries to 2 indices. So you say then 1,1. So you can match 1 to 1 to 1 2, 2, 2, 2, 3, 3, 2, 3, 1, 3, 2, then it gets complicated. I think 2, 3 to 5, 1, 2 to 6, what's left, 1, 3 to 4, something like that. So all the so 4 is a shear component, and 1 is an axial component, right? So you can say you will have, so this tensor will only have components of 1, 1, 1, 1, or 4, 4, 4, 1, 3, 1, 3. That's the only possible numbers there are. And all the shear components are the same, and all the axial components are the same. So this is just the symmetry that you have. You can just simplify the whole tensor to just 2 numbers. Right? Yeah, I know it's hard. I also don't know how to explain this on the board. Maybe I can try to do that later. Okay. Okay, so far? Yes, okay. Good. So, I mentioned the 0-point fluctuation strength, and this is actually just a property of the mechanical resonator, right? So the mechanical resonator can be decomposed into mechanical modes, which are some pattern and harmonically oscillating amplitude. So this pattern is normalized to 1, as a magnitude 1, then the maximum vector here is 1, and this one just obeys the harmonic oscillator equations. Which also means that this is the classical description, that we can introduce an operator, which then is harmonically quantized. And if we want to know the strain, we just put in this relation into here. This is the definition for the strain tensor. And if we want to know what's the smallest strain modulation, we have to use the 0-point fluctuation displacement, which is the variance of the standard deviation, quantum mechanical standard deviation of your x. So this is then what you get out of it. This is the 0-point fluctuation term, and the strain is just the one you can get from this normalized vector. And here I wrote directly that we take the maximum because we want to put our atom at the maximum spot in the resonator. Okay. What you notice here is in the 0-point fluctuation term, we have the resonance frequency and the so-called most effective mass. This is not only the mass of the mechanical resonator, it's the mass of the mode, so to say. And you can understand it as some kind of variance of the mode displacement. So you have you integrate over the square normalized displacement of the masses and multiply by the density if it's constant. If not, you just have to put it in there. Okay. So this is the important quantity. If this is large, our coupling is large. Right. So I want to go through one example. Which was the first example I calculated in my thesis. And it's quite simple geometry of just a thin clamped beam. So it's a beam, it has a height, it has a width, it is fixed at 2 ends, and yes. And we have to assume that the length is much larger than the thickness. That ensures us that we only have modes really in the longitudinal modes and no modes in direction of the beam or torsional modes and so on. This makes it much simpler. We can model this by only the displacement of the central line, basically. Yeah, so, in the real experiment, we also have to ensure that the crystal axis is exactly in the specific direction. So, for example, we have to select x in the direction 101, and z in the direction -101, and y then can just be 0, 1, 0, and the B field also in this specific direction. Also, again, we just use silicon. Yes. Okay. Nice thing about this is, I mean, this is why I selected it. It can all be done analytically. Right? You get out nodes that really look like sinus. It's not exactly a sine, but they look like this. And we'll skip this. The strain then also looks something like this. So you have, it's basically like the second derivative of the displacement curves, roughly. These artifacts here are a bit because I used the central derivative on the analytical results, so unfortunately it's still there. But what is interesting is that the strain in the resonator is highest at the sides, right? So we assumed mathematically rigid boundaries, and the strain is highest at the sides. So the question is this physical? Like, would this also happen in a real experiment? And for that, I then used a finite element solver, console, and built this model. It's all parameterized in the thickness of the beam to ensure that it's stable when tweaking parameters. And you see that now the boundary is actually also modeled. And for the meshing part, which is a bit annoying, you also have to make sure that it's really fine at the boundaries, which is not always done automatically. So the result of this is then the strain looks like this. So this peak is somehow real, I would say. You can look closer, it's still some weird spike, but if you compare, this is maybe 1% of the whole peak, so we can just neglect this as an uncertainty. For now, it's just important how large this overall peak is. Okay, so great, we can look at two peaks. We can look at the center peak, which was in the middle of the beam, and we can look at the peaks at the sides, right? We can look here, and we can look here, and these are two possible spots where to put the atom. For the thickness, we have also to keep in mind that this one is much thicker, so if the beam is very short, then it's probably easier to put an atom here than here, because there's roughly an order of magnitude between the thickness of these two maxima. Okay. So how does now our zero-point fluctuation strain vary if we modify our geometry? We can make the thickness wider, and we can make it longer, right? It doesn't make much sense to think about the ratio of thickness and width, because as you see, maybe I went a bit too fast. As soon as we increase, for example, the width and keep the length constant, our zero-point fluctuation decreases. So that would mean that if we want to have the best possible beam, we have to make it the thinnest, and then it doesn't make sense to increase the other dimensions. So we just set them equal and as small as possible. And for the length, it's also not really surprising, I think, that it also decreases. If we make it longer, so technically we have to make the beam as small as possible to increase our coupling. But what I didn't mention so far is the frequency. The frequency is given by this formula analytically, it roughly holds. And you see that the thickness or the height of the beam is linear in it, and the length is 1 over L squared. So we have to make this beam as if we want to, if we decrease the length, the frequency will go up really a lot. And that's actually a problem. The problem in it is, it is a problem because, as I've mentioned before, we have to modulate our Hamiltonian, so by the frequency of the transition. The transition is determined by the magnetic field. And we can only have finite magnetic fields. So let's assume we can only produce 10 Tesla. It means that we cannot go over a certain resonance frequency, because then we couldn't drive our nuclear transition. So we have to find a different way to display our coupling. And for this, I want to look at this graph. So we have the coupling strength at the y-axis and the resonance frequency at the x-axis. And then we can look at what constraints do we have. So first constraint is mentioned. So the resonance frequency cannot be larger than the gyromagnetic ratio of our atom, for example, here in germanium, and times 10 Tesla, and then we would end up at something like 14.9 megahertz. On the other hand, we also have to make sure that our strong coupling is maintained. So our coupling rate has to be larger than the loss rate of the nuclear spin. This is typically in the range of 3 Hertz. This is data from antimony, but for the other donors, it's probably in the same range. For germanium, it's hopefully better because it's a donor, but for now, we just assume it's the same. Then, also, we have to assure that our coupling rate is much better than the loss rate of the mechanical regulator. This is typically described by this quality factor. And to get the loss rate, you have to not divide frequency by quality factor, which gives us something dependent on frequency. Right? So if you put this in, you get these two lines. This is the line of the nuclear spin, so we have to be above that one, and we have to be above that frequency-dependent line. So in this region. Okay. So now we can draw in where our mechanical resonators will end up. For now, we just use germanium, and if you just assume a width of 13 nanometers, which is hopefully possible to fabricate, we end up here, which is unfortunately very far away from where we want to be. It's like maybe 2 orders of magnitude, almost 2. Okay, you remember if we decrease the width, we can get higher. If we increase it, we go lower. So with 10 nanometers width, we are still too low. So okay, let's put it to the peak. How far do we have to go to be in there? And it says 1 nanometer width. So okay, if you can fabricate a 1 nanometer beam width, congratulations, we solved the problem. But I don't think this is possible so soon. And we have to just think realistically that the 13 nanometers is probably what we can get with germanium. But there are still the other atoms. First, before we go to that, let's check what happens if we increase the mode index, right? This is just one mode. It's the fundamental mode of the beam. What if we increase it? Oh yeah, sorry, I went too far ahead. This is just the length of the beams in there, so you can now read up how long the beam is. And you see that for a realistic beam, we would be somewhere in the range of 1 to 3 micrometer length, but still very much too short beams, much too thin beams. Right, okay, so now let's look at what happens if we increase the mode index. So, yes. So each of these crosses now represents increasing the mode index by 1. And you see, although that the coupling increases, the frequency of the resonator also increases, but it increases more than the coupling. So what we actually get is that the curve here is flatter than any of the fundamental mode curves. This means that, unfortunately, any increase in the mechanical mode won't help us here. So we can just stick within the fundamental mode and have to try to get into this region. Because if you imagine, for example, that this curve would be here, this is much flatter than the fundamental mode, and we unfortunately cannot go higher than with the fundamental mode. Okay. So, okay, what's left is to look at our best atom. I mean, this is germanium. Bismuth is much better. And if you look at the results, you also have to consider like the general magnetic ratio is much higher, so this red line is shifted to the right. And also the coupling factor is much higher. So if you look at the 30 nanometers width line, we are almost in the strong coupling regime. It's almost, I mean, if you could improve the mechanical resonator by a lot, you would already be in the strong coupling regime. But if you are able to build a beam that is 10 nanometers thick, you are even in the strong coupling regime. So this is great. I mean, this actually means that this is possible. It's just a matter of how hard you can work in a clean room to build this structure to make it very coherent, to realize the system. Cool. Okay. So to sum up, I already told you it's great. You can show that at least even for germanium that it's only a matter of 1 or 2 magnitudes, but for bismuth it's even in the coupling regime, strong coupling regime. For here I can also tell you that for the reason why you also put in germanium is that in contrast to the earlier for the works of the Moreno group, it's a neutral atom. So we expect that because of the missing electron, the missing extra electron, the coherence is much better. Unfortunately, this is also affects somehow the coupling to the mechanical resonator, and we would need to work harder there than, for example, for bismuth. And I think the only thing that I haven't talked about is, for example, that here we only have this limited set of data based on these values of donors and silicon. But maybe this is even better with other host materials. We don't know. Maybe even something like quartz is good. There are many resonators in quartz, but we don't know how donors are working in this material. So maybe there's still a lot of room, and yeah. Right. Okay. So other possible research directions in this field. So this is just one example. First, I could look at more resonators. There are cantilevers, so like this one. So just cut off one end. I've already done this. There's a factor of 2 in there, so you will get another factor of 2 in coupling. The beams get shorter, which is also expected, I would say, because the resonance frequency is much higher if you lose one end. You can also think about using those dumbbell resonators, although these are really macroscopic, and you can find out that the overall scaling of the coupling is 1 over L squared with the length. So for coupling to a nuclear spin, this is rather unlikely. You can also try to look at torsional resonators, or even something like surface acoustic or bulk acoustic wave resonators. But my feeling is that these are really lossy. And the other completely different field is looking at how to read this system out, how to build this actually, because there's still a lot of open questions on how actually to find out what is the nuclear spin state in this system. Yes. Yeah. With this, I want to thank you. I hope you take it.
Oh, it's all right. I'll try to finish in another 10 minutes, okay? Questions for Sebastian? I think it's pretty crazy, right? Like, I don't know what is really good for this system, just the thought that you can potentially couple a single nuclear spin with a single phonon in a mechanical resonator. I think it's really elegant from a physics viewpoint as a demonstration experiment. Yeah, for us, this is the big question now. This is, of course, super different. It's really at the edge of what is possible, and I think if you really want to do it in the lab, this will be a decades-long research line, if this is possible or not. But I think on the way you will decide if it's worth continuing or not. So we're sort of toying with the idea. Like also in the Morello group, we are sort of moving in this direction a little bit to see if this might be possible or not. Just because it's, I think, such a nice implementation of phone coupling potentially.
Any more questions?
If no questions, the last thing, and I'll just continue. Thanks so much. So this is the last thing that I want to show, and it sort of links back to the first lecture on quantum dots as well a little bit. So I think it's worth quickly showing this. All I showed you so far on these nuclear spins in terms of experiments was on donors. But what is the donor? It is a nuclear spin with a hyperfine coupled electron, right? And it's just convenient when you have a donor that the system comes together at once. But we can also, instead of that phosphorus atom, use an artificial atom, namely a quantum dot, to have hyperfine coupling between a nuclear spin and a quantum dot. So that's this experiment. So I want to give basically I copied the slides from a presentation from Bas. I know Bas very well. We studied together. He's now in Leiden, and this was basically one of his main projects during his postdoc at USW. So we overlapped there, and he was in the other group, and he did this experiment. So now we change to CMOS quantum dots. So we work on the same type of substrate, natural silicon with a thin layer of purified silicon. This is not the right number, I think. This is, oh yeah, this is it's about blue oxide, that is the right number. We have a tiny field oxide here, 10 nanometers, tiny gate oxide, sorry, and we put a whole bunch of electric gates to define our quantum dot, okay? So we have this gate that defines the dot here, so the dot sits underneath here, and then there's all these other control gates. The yellow one here forms the SAT, the charge detector, to do spin to charge conversion, and these are additional control gates. Here we have the microwave line. So across spectrum it looks like this. This is the device. And you can find a double dot underneath the gates here. Pretty difficult, pretty hard. It's sort of at the edge what you can do in an academic clean room, I would say, but it's possible. Alright, then we have, of course, our control electronics, right? We monitor the current here for the spin to charge conversion. Just that's, in that sense, it is very similar to the donor electrons. It's just that now our quantum dots are defined here. This is all possible. That was demonstrated before our time, 2014. The same type of spin to charge conversion, doable. You can drive them using the RF line. You get Rabi's. You get pretty decent coherence times for a spin qubit. Okay, this is quite good. With dynamical decoupling, it gets well into the tens of milliseconds for an electron spin. You can do the individual gates are really good. 2-qubit gates by now have also been demonstrated in one of these devices to be really quite good. Problem with this whole platform is scale, right? How do you tackle scale? It's very difficult. Not entirely impossible. I discussed that the other day. So the idea is, this is now this idea again from Bruce Kane about the donor-based spin quantum computer. That you get rid of the donors and you put the nuclear spins right at the interface where the electron quantum dots sit, and you make a quantum computer that way. Okay? Then the idea is that, of course, nuclear spins, we have all these attractive properties that they are so well isolated and well behaved, but of course they're also very slow. And then we have the electron spins for fast operations to have connect the nuclear spins. Maybe do something with long-range interactions, and potentially, if we solve the engineering fabrication challenge, potentially scalable. Now, what Bas did in his experiment was this is the center of the ESR frequency, so driving the nuclear spin, the electron spin, in one of the quantum dots. And what they saw was that the frequency was jumping. And that is the signature of a hyperfine splitting. So there is another quantum system coupling to the electron spin that makes the frequency jump. Okay, so you bin this, you see that you have two distributions. And the idea is that although we isotopically purify the substrate, we are at a level of 800 ppm or so. So that's like a little bit less than a promille of silicon-29 left in the host lattice. So this is all silicon-28, but you do the math, you find that every now and then you still have a silicon-29 spin. And it overlaps with the quantum dot wave function. And you can do some estimations, given the quantum dot diameter, how much the wave function is spread out or not, given that you have a certain background concentration, what type of hyperfine interaction strength do you expect? And they are in this type of 100 kilodalton range. Okay? So from these estimations, given our residual silicon-29 concentration, we know that each and every quantum dot in silicon MOS should couple to 1, 2, 3 nuclear silicon-29 nuclear spins. And the game is, of course, that you can now utilize these. You can actually address these nuclear spins. And this is actually very similar to what people did before in NV centers. If you are familiar with research in that community, in NV centers you can do exactly the same thing, where the electron spin wave function overlaps with silicon carbon 13s in the diamond lattice. There people have done it up to about 20 C13 spins that they control that way. This experiment shows it for 1 silicon-29. Alright, so this is really the same game that you can do conditional, you can do, given that you know these two frequencies, you can do conditional ESR pulse while you are driving the nuclear spin using an NMR pulse. Same game as at the phosphorus, and indeed they found that they had an NMR frequency that they could drive. And this is, when working with nuclear spins, this is sort of what you really need to do. You need to measure the exact position of your NMR frequency, do it as a function of the magnetic field, and then you can fit it to the nuclear diamagnetic ratio, and that is how you determine what nuclear spin you work with. This is an extremely well-known established number for all isotopes, right? So once you get this number out, you know what spin you are dealing with. This is also how we make sure that we have a phosphorus or an antimony donor. It's our sanity check normally. Measure the nuclear diamagnetic ratio. So this was all nice, and then yeah, they can get, you do the readout, you do it a bunch of times, not once, but a bunch of times, and you can crank up the readout fidelity to really high points. So you can really control and read out these nuclear spins. This is done in a double quantum dot device here, so the readout they use is basically based on Pauli spin blockade of a singular triplet state. The details, I kind of showed you that in the first lecture, if you still remember. Details don't matter so much. Point is, yeah, you can detect this, the electron spin, and then map the nuclear spin onto the electron spin. Yeah, they showed that they have Rabies, they can do all that. There's a little bit of a difference where exactly the electron sits. If it sits on the nearby dot or on the further away dot, you get slightly different T2 stars. I think this will vary basically from quantum dot to quantum dot and from nuclear spin to nuclear spin that you address. So in that sense, it is a stochastic property given by the device that you have. They found a second one that they could work with, a slightly lower hyperfine coupling, slightly better coherence times. In any case, it's a demonstration that this idea can work. So the idea is then really that you try and build something like this. It looks pretty crazy when you draw it like that, given where we are today, but I think the idea is neat, that you have electron spins as ancilla qubits that you use for transferring quantum information and applying conditional gates, and the data qubits are your nuclear spins. Okay, so it's sort of serving as a quantum memory. That is, I think, the vision behind this. And why I wanted to show you this, these two possibilities, donors versus quantum dots, to access nuclear spins in materials like silicon, is that they both have, of course, their pros and cons. So for the donors, the nuclear spin of the ionized donor is slightly more coherent, it seems. Although I have a feeling that if you cycle enough devices, this may be, you may get good numbers here as well. Question is, of course, from an engineering perspective, if this is an attractive enough number that you get on average. Another thing is that the donor devices, we are already there. We can control these nuclear spins really well, large nuclear spins. So the control and the fabrication is a little bit easier. But this doesn't scale. I commented on that in my first lecture. Very difficult to make this scalable. Here we have scalability very hard, of course, from an engineering perspective, but it seems feasible. We can transfer this to other elements. We can, instead of looking at silicon-29, we can deliberately put in a little background concentration of 73 germanium, or even locally implant that, and at the position where a quantum dot will sit with a 10 nanometer resolution as possible. And that is a nice one. That is one of these large spins that I really like. So this is a 9.5 one with all the counter core, etc. And this is also why I wanted Sebastian to really look into germanium as well. And this idea is also transferable to heterostructures, potentially. I'm a bit surprised that nobody has tried this yet in silicon germanium. I think it should be possible. Germanium is, I think, unknown as yet. The main problem that you have with the donors is this one. Okay? The tunnel rate from a reservoir to a donor is basically very difficult to control. And in any case, because the hyperfine interaction is of order 100 megahertz and tunneling is a stochastic process, to not introduce a phase error in your nuclear spin, you would have to measure 100,000 times faster than the hyperfine coupling. Then you can exactly know when you turn on the hyperfine Hamiltonian and correct for any phase errors. Now I'm talking about a 10 to 100 gigahertz measurement of a tunneling event, and that is not realistically possible. Or a loading or a unloading event, and you need to apply gate process that's just not feasible in experiment. Here, however, the hyperfine is weaker. It's between 100 kilohertz and 100 megahertz, meaning that we need to be able to turn the hyperfine on and off at a gigahertz range, and that is possible and actually, in fact, already done in this experiment. So long term, I think that this platform allows for much more subtle schemes where we could do a partial readout of nuclear spin, down project it into a smaller superposition, keep it phase coherent, load another electron on, do feedback, etc. All these sort of games. And that I don't see that happen for donors. Now, what I want to end with is error correction using these nuclear spins. It's too fresh for me that to make a nice few slides or so on it. Like, I have not thought about it all that much. So what I did is I just copy pasted from the paper a few relevant sentences. This is the same paper that I showed you the cat stakes from before. The important thing is that we have now an eight-dimensional Hilbert space in which we can encode quantum information. And actually we can do tricks to correct the quantum information in an efficient way. Okay? It is stupid to keep working as if we have a spin 1/2. No, we have a spin 7/2, 8 dimensions. So, one idea is that you implement an error correction code really geared towards a QDIT, a larger dimensional object, and you can correct phase-slip errors. Okay? Which I think is nice. You encode quantum information that you can immediately with using the same object error correct. Another idea is that you correct for rotation errors. So this is for that minimum size you need is a 7.5. Yeah. So the point I want to make here is that basically we're collaborating with theoreticians. I'm not so much with Andrea, is for sure with people that look into error correction, etc., to come up with clever encoding schemes and syndrome measurements, etc., so that you can do an efficient error correction of a logical qubit encoded in an 8-dimensional Hilbert space. Okay, and actually there are some interesting ideas. That's sort of the point I want to make. There are some schemes already being put forward tailored towards these nuclear spins that may allow for that. So in that sense, yeah, this of course the devil is in the details, how accurate you can control all this, etc. If this is scalable or not. But in principle, I think this is a really neat blueprint in the long run to have this, to have these local, very localized higher Hilbert spaces. That you can access through electron swings in a phantom dot. Yeah. So with that, I would really like to close off the whole lecture series. I hope you found it somewhat interesting and entertaining. I think they are really cool objects. It's a little bit niche, of course. We need to be honest about it as well, but I do think that they are very nice objects. They're highly coherent, exquisite control. We can do fundamental quantum studies in there, like study nonlinear quantum dynamics. Sebastian's presentation on the topic of that, I think, is just such an interesting, crazy idea that we can potentially pursue based on this whole body of work. Yeah, we can, in principle, dream of a scalable platform and a quantum computer where this is integrated into. New error correction scheme. So I think the study of these high-spin nuclei in silicon has really opened up a whole avenue of follow-up research that will keep a few research groups, experimental research groups in the world quite busy, I think, for the next decade.
That's it from my side. I have a final thank you slide, and I want to say a few more words, but I want to do that afterwards. Let's first do maybe questions about this presentation. Anything else science-wise that I presented? Okay. Oops. Wrong mouse. Too many mouses. I'm just stopping the recording.